The project I will show here is a simple framework to solve a hard problem. So what is the hard problem? If you see the network in here, that is just black dots and links, I will use it to describe the problem that I am working on right now, that is constraint satisfaction problems. So a constraint satisfaction problem is a problem defined by a set of variables, and each variable can take any value in some domain. And you define a series of constraints in the values that these variables can take. So any problem in the world that you can describe in this way, so the values that a variable assumes depends on the variables of any other, you can map in a constraint satisfaction problem. So this is a very simple description, but it belongs to a very hard kind of problems in computer sciences that is called non-deterministic polynomial time problems. So in computer sciences, you solve problems or define algorithms efficiency depending on the time that you take to solve this algorithm, depending on the number of variables that you have. And if this time depends polynomially of the number of variables, the algorithm is efficient. If it depends exponentially, for example, it is intractable, which means that you can need more time than the age of the universe, for example, to solve a problem that is so simple as, for example, Sudoku, if you want to explore all the possible configurations. So we have a combinatorial problem now, and there has been approaches to this from a long time ago, but from the neural point of view, the first approaches were in the 80s by Hopfield, trying to use artificial neural networks in the beginning of artificial intelligence to solve constraint satisfaction problems like the traveling salesman problem, where you try to find the minimum path to go through several cities in the minimum time or cost of your travel. So what I use to solve these problems is instead what is called spiking neurons you are very familiar with that. And these neurons were applied to this kind of problems only recently by Havenchus. And well, there are some subthreshold approaches as well from the labs in Zurich, from INI. But what I use to solve the problem is the Spinnaker system that you see here. The Spinnaker system is a machine of several processors, like chips like this one that you see here, that have several processors, and these work in an asynchronous manner. They don't work like a conventional computer, and they mimic more the brain. So it is a spiking neuron approach to constraint satisfaction problems. So the strategy is very simple. You take each variable of your problem, each domain, you create a neural population, and you create inhibitory connections between neural populations to represent a constraint, or you create excitatory if the constraint is that the values should be equal. So it's a very simple description, but it allows you to solve several practical problems that are very interesting or simple to understand, and from there you may be more related to neuroscience, can understand how the brain makes approach constraint satisfaction problems in perception, for example. So what I used was take this neural network, put noise in it, and see if it can search through the state space of this problem to find the correct solution for a problem. So one of the problems that I saw is this one in here, that is called coloring map problem, in which you try to find, you have different regions in a planar graph, and you try to assign a color to each one of these regions in a way that you don't have two bordering countries having the same color. So it's a very toy problem, but it is applied in computer sciences for example, resource allocation when you are building processors. So in the B part of the figure, you can have the graph of this map, and you map that to a spiking neural network. And this graph in here is the entropy of the network. That is the Shannon entropy indeed. Is how many information do you need to describe the network state? So how many binary digits do you need to describe the number of states that you have? So you see that the entropy is going down till in the blue region, it converges to the solution of the problem, making a stochastic search over this state of possible states of the problem. And it indeed solves a problem that is hard, and although is solvable in conventional computers, well, we are still exploring the computational abilities of spiking neurons. So in the right, the bottom part, you see how the domains of these variables are competing between them when you have the different populations saying that, that was very quickly. But anyway, you can apply that to other problems like Sudoku, or spin glasses. That's all. This is just the statistics of convergence of the problem. And yeah, that was the